Recording's live. Good to go.
Okay. Yeah, so this is the meeting regarding chapter 3. It's the heaviest, I guess, in terms of math chapter. And we'll start with a review of the previous chapter, just to go over the main topics that we covered, which was radiometry, the main equations, and that really sums it up. So what we saw last time was, okay, we need some notion of quantity that we'll measure, and these quantities measure different things. For example, if we have a pinhole camera, we would measure irradiance, because if you consider the aperture of the camera to be a single point, then you have a single point, but you have a whole set of directions. Well, this is the definition of irradiance. Now, for instance, if you consider an orthographic camera, you're measuring intensity at each pixel, simply because you consider only a specific direction, which is orthogonal to your film. Finally, if you consider a camera that, let's say, has a lens or it's not pinhole and it's not orthographic, so you consider both a set of directions for each pixel and it has an area that is non-zero, then you can simulate effects such as depth of field, and you are really measuring gradient flux. Finally, like in the real world, your camera has a non-infinite shutter speed, so it takes some time before you can measure. So you measure your energy over some interval of time, not in a single point in time. So what you measure there is radiant energy, and this allows you to model effects such as exposure and motion blur. So these are really the quantities. Obviously, at the most fundamental quantity that we'll talk about is incident radiance, or also even more fundamentally spectral radiance if you have a spectral renderer. If you don't, well, usually to be more efficient, a person would take the spectral radiance and integrate it with respect to some color matching function. So you can follow this link to find such color matching functions and get some kind of trichromatic radiance, which is not actually radiance, but it's something we do to optimize things. Questions on this part? I guess not. Then we will continue. Last time we saw the Brdf, which is really the differential outgoing radiance over the differential irradiance incident, and we could write this in that form. Now, if you move this part here and you integrate both sides, well, you get the rendering equation. And we could rewrite the rendering equation over not only over solid angles, but also over scene surfaces. So here M is the set of points of the scene surfaces, and these two are equivalent. This can be used to more efficiently sample, let's say, BSDFs, your materials, and this can be used to sample more efficiently your light sources. Finally, we saw the measurement equation, which really tells you, okay, how much energy do I get at the sensor? So as I mentioned, this doesn't need to be always flux, so one of those integrals can disappear, depending whether, so for example, if you have a pinhole camera, then this integral would disappear simply because you have a single point. And if you have, and this would turn into intensity. Now, if you have into irradiance, now if you have an orthographic camera, then you have a single direction, so this integral would disappear and you would be measuring intensity. And obviously, if your pixel has both an area and it has also a whole set of solid angles, then you're measuring flux. And you can rewrite the same integral here by introducing a function that is 1 only on these sets and 0 everywhere else, and then you can rewrite your integral with respect to all scene surfaces and all directions. This is simply for convenience. So at the end of the day, when you're writing a ray tracer, you really want to measure something like that. And to measure something like that, you have an unknown function L, which you need to somehow estimate by using these equations. So today we'll look at how we can solve these equations numerically. Questions? No questions, okay. Then yeah, what's the motivation for today's topic? As I mentioned, we want to be able to solve these equations here. And in chapter 4, we will see that the formal solution can be written as a sum of integrals. And these integrals have a nice interpretation. So that is a direct light coming, let's say, towards your sensor. This is light from one bounce away. This is light from two bounces away, etc. And I can show you an example of this. So let's say you have your scene. So that would be direct light. That would be here from one bounce away. That would be from two bounces away, from three bounces away. And as you can see, the energy generally decreases. So in practice, we can not take the sum until infinity, but until some depth that we decide, okay, that's a good depth to cut the energy, because at some point it's just so little that it doesn't make much a difference. So these terms we'll see in chapter 4 are really integrals and increasingly dimensional. So that's a single integral of the surfaces. That's a double integral. Then you have a n times integral, etc. So you get a sum of increasingly dimensional integrals, and we will see how to numerically estimate each of those separately. So this one, then this one, etc. Yes, questions? No questions? Then we'll continue with numerical integration. In the general setting, we would have an integral with respect to some function in some d-dimensional space. So as you can see here, for example, the surfaces, this is 2D, this is 4D, this is 2 times n dimensions. So in the general setting, we want to estimate highly dimensional integrals of this form over some set D. In the previous case, it was the scene surfaces. And what we'll see in the current section is that you can do that simply by taking a sum where you just picked some points in your domain and you took the average and multiplied by the size of the domain. So we'll see that, okay, this gives you an estimate of the integral. And if your sequence of points that you take is nice, so in some sort of sense uniform, then by increasing the number of samples, you get closer and closer to the true solution. Okay, let's look at a very simple example of having n numbers, real numbers. So you can think of 3.14, 2, 5, 7, whatever. And the average of these numbers is simply their sum divided by the count of these numbers. Now we can do the exact same thing if we have a function, a discrete function. So we have a finite discrete function. We have n arguments for the function, and to each argument it gives you some, let's say, real number. And once again, it's the very same thing. To compute the average of this function is to sum it up on all arguments and then divide by the number of arguments, or the size of this set here. Now, if you have a function that is defined on a continuous domain, so let's say some interval AB, and once again, it's in the real numbers, then the equivalent to the above is simply taking, rather than a sum, something like an infinite sum, an integral that is from A to B of this divided by the size of the interval. So this is just the length of the interval here. Questions? No? So these are just averages that we are computing. And let's see another example. So say you have a function defined on a 2D disk, so in 2D space, and your function gives you a number for each point of the disk. Then once again, the average is simply the integral over the size of the disk. In this case, it's the area. Here it was the length. And if we look at the general setting, it's the d-dimensional measure. So in 1D it's length, in 2D it's area, in 3D it's volume, in 4D it's 4D volume, etc. But the idea is the same. You have the integral of the function divided by the size of the domain gives you the average. Now, why is this useful? Well, because the average, like we saw in the very beginning in the discrete setting, it can be approximated simply by taking the average of the function at sufficiently many locations that are of points that are uniformly distributed. They don't need to be random. It's enough if they are uniform in this domain D. So that gives you the average of the function. Well, why is this useful for computing the integral? Well, because the integral was really the average is equal to the integral divided by the size of the domain. So if you rewrite this, you can write, okay, the integral is the size of the domain multiplied by the average. And the average we can approximate. So we get an approximation of the integral of this form. Questions on that? Okay, I will assume everything's clear. So in the general setting, we would have a, let's even consider just random numbers, but not necessarily in 0, 1. And you can make a high dimensional random number by just taking a random number for each dimension. So you can construct a random number. Let's say you take R1, R2, and R3 in 0, 1, and then you use each of those as dimensions. Then you have a 3-dimensional random point in 0, 1 cubed. That's a problem because, okay, we were talking about general domains, and as we saw in the rendering equation, the domain is either upper hemisphere or a set of surfaces, surface points. And in here you can see, okay, some general domain D. While what we have from, let's say, our pseudo-random number generator is just a point in 0, 1, or the 0, 1 hypercube, so a D-dimensional hypercube. And to basically estimate such an integral, we will need to somehow transform from this, which we showed that we can estimate, to this. This one here, if you remember, we had this measure here, but the measure, so the volume of 0, 1, the d-dimensional cube, 0, 1 unit cube is really 1. So this is why you have a 1 here instead of this. So we know currently how to estimate such integrals, but not such integrals, simply because we cannot have uniform points in this arbitrary set D. So how can we deal with that? Well, you can construct a mapping, so a function from our domain where we have our, let's say, random numbers to this set D. Let's just assume we have such a function, which given a point in this unit hypercube gives us a point in D. Then substituting, so we have our original integral, and we know that, okay, x1 prime is this, xd prime is this, so substituting in here, and also in the differential, we get something that's very close to what we want. So we want to have something like that. But the differential here doesn't look like what we have here. So we need one more step. We need to relate this differential to this differential. And this is a well-studied subject in mathematics, and you can show that, okay, you can relate this, you can turn it into that simply by taking the absolute value of the determinant of the Jacobian of the transformation. Now, if that is hard to grasp, don't worry. We'll have examples of this, and this is really the theoretical part. So even if, let's say, you don't know what the Jacobian is, that shouldn't be a large issue later down the road, especially considering we have these derived anyways. Yeah, so at the end of the day, you start with your original integral, you apply some transformation, then you get your original domain, and yeah, this should be to the power D here. That's a typo. And finally, you get a function g, which is of this form. And in this, we know how to integrate. It's simply that. So we transformed our function into a new function, which we can integrate with our methods. So what do we need for that? Well, we should be able to evaluate f at points, but that should be fairly easy in the cases we consider. We need a sequence of points uniform in 0, 1 to the power d. So that is that we will get through our pseudo-random number generator, and we'll need a differentiable mapping t, which we'll see how to derive, for example, for the unit hemisphere, or also for picking points on the scene surfaces, etc. Questions? I mean, feel free to interrupt me at any point if there are questions. Okay, if there are no questions, let's continue to the probabilistic interpretation of this. So probably what you've seen for the most part in the book, and it the relationship between this Jacobian here and the probability density function it's 1 over this Jacobian. So, and with respect to the old parameterization, so with respect to points in D. So it's just a reciprocal relationship. And this mapping that we saw, that we required, is really the either you can think of the mapping as the inverse CDF, commutative distribution function, or you can think of the commutative distribution function as the inverse of this mapping. Yeah, so some examples, for example, take points in 0, 1 once again in the unique hypercube, and take another box. So this is a Cartesian product here of these intervals, and we want to construct a mapping from this to this, and we can do that simply by having this transformation for every point, and you can verify that, okay, if I plug in 0 here, I get AK, and if I plug in 1, I get BK, so I get exactly what I want, the interval. The Jacobian of this transformation it's a diagonal matrix with this on the diagonal, and this is, if you take the determinant and you take the absolute value, this is really the volume of this box. So it gives you the factor that you need to multiply this volume to get the new volume. Now, constructing the function g that we talked about, which is really f multiplied by this, you get an expression for the integration in such a domain. So this is just an example of the theory that I talked about. In a similar fashion, you can take, let's say, the upper hemisphere, parameterized in, say, spherical coordinates, and assume that you want to compute an integral like that. Or we can also parameterize it like this. So we want to find a relationship between a point in 0, 1 in this cosine squared theta, and a point in 0, 1 and pi, which is in 0 to pi. We can do that with, say, a transformation like this. We can compute the Jacobian, get to pi, and then again we can write an estimator for that. So even if we don't know how to analytically integrate f, we can always write a sum, so we can integrate it. Questions? Michael, can you mute yourself?
My apologies.
Thanks. Yeah. So what does this bring? So such a mapping. Generally, it allows you to go from 0, 1 to some domain, but also it can be used to decrease the error of such estimators. So basically using less samples to get a similar error. So how can this be done? We can take as an example the ideal transformation. So the ideal transformation would have a Jacobian, which is the integral divided by the function. Now, if you plug it in the estimator, these cancel out, and you're just left with the integral itself. So that would mean that you would need exactly one sample and you would have the correct solution. Generally, in practice, you do not. Obviously, this required knowing the solution. In practice, you do not know the solution, but maybe you know a good approximation of f, of the integral. Of, for example, you have an approximation of f, some function, let's say q, and you can integrate it, and then you can use that to perform importance sampling. Okay, we'll skip that, not very important. Yeah, here's an example of this. So assume that you have a function f multiplied by h. In your rendering equation, let's say f is your Brdf and h is your light energy, so your radiance, or vice versa. This is the radiance and this is the Brdf. And you say, okay, I know how to integrate the Brdf, so I know how to compute this integral, and I can construct a transformation such that its Jacobian is this over this, but I don't know how to integrate analytically the product. So what you can do is, okay, construct this transformation, plug this in here, and h, so let's say here your Brdf would disappear from the integral, hopefully decreasing the error of your estimator. So your new estimator would require less samples. So something like this would require less samples than just creating an estimator directly from where is that? Directly from this. So just sampling F may be more optimal than sampling both of those. It could also make things worse, but in general, we would try to do important sampling where it makes sense, or where we get a good approximation. Questions on that?
Regarding using the approximation function to reduce this error.
Yeah.
Do you know of any other hints to find this approximate function?
Oh yes. So there's the topic of path guiding.
Okay.
I don't know whether you're familiar. So what path guiding really does is where it says, okay, I have this product, right? And I approximate this product. So it's not exactly that, but I approximate something like this, and then I can sample that. So path guiding, technically, importance samples both of those. Your usual importance sampling that you've seen, like sampling the Brdf or sampling the lights, that's like picking one of those and removing it from the integral. So what you see here. But path guiding is kind of trying to sample both. Does that make sense?
Yeah, kind of. I was thinking of, because really we have equation 36. Yes, it's 36.
I want to, okay, let's get back here. So you can see the solution is something very ugly, right?
Okay.
The solution of radiance. And generally, you cannot analytically compute this. But for example, you can get rid of those terms through Brdf sampling, or you can get rid of, let's say, those terms through area light sampling and stuff like that. If you had some visibility structure of your scene, then you can get rid of the visibility term, etc.
Okay, regarding Brdf sampling, it doesn't really matter if it's analytical or empirical, right? Or does it really matter in this case?
What do you mean?
I mean, if the Brdf you can only compute it empirically, for example, does it really help you finding the?
So if you have a if you have a lookup table,
Sure.
that's not a problem. You can build a CDF of the, so you can always, so for example, you can have BIDFs that are analytical for which you cannot compute the analytical integral. But for every tabulated BIDF, you can compute the integral. It's just an integral image or whatever hyper image, and then you can sample it ideally. So for any tabulated thing, you can actually sample it perfectly.
Okay.
In that case, you know the exact integral. For some analytic BIDFs, you cannot get the whole integral. Like you can get parts of it, let's say the NDF or whatever, so sample regarding something, but not ideal.
I see. Oh, thank you. Thank you.
Other questions? Okay, then. Yeah, okay, I already mentioned the BSDF sampling area lights, and you can, for example, you may be able to integrate F and integrate H separately, but you may not be able, let's say, integrate those both. So what you can do is you can integrate that, make one estimator, then integrate that, make another estimator with two probability density functions, or equivalently two Jacobians, and combine the two estimators using multiple importance sampling. And we'll see what this is right now. I think we should do a 5-minute break right now because 25 minutes passed. So see you in 5 minutes. Okay, I'm back. I think there's one more minute, so I won't rush it. But yeah. So just to reiterate what I said before, so the main goal of, in this case, importance sampling would be to get rid of some of those terms. So find a probability distribution or a Jacobian that cancels out some of the terms, possibly the BRDF, possibly all the BRDFs in higher dimensional integrals, possibly the visibility or something else. So ideally, we want to remove some terms that we know how to integrate, so they don't factor into the final error. So we make full use of the knowledge that we have, that okay, we can integrate that, and it can disappear from the estimator in that sense. Okay, so are there questions before I continue with multiple importance sampling? I guess not. Yeah, so what is multiple importance sampling about? Say that you picked one transformation T1, and then you picked another transformation T2 for your integral, which was something like this. So let's say you had two approximations of your function f, some f1 and f2, and for these approximations, you generated a transformation that yielded that function as a reciprocal Jacobian or as a probability density function. And then you get two estimators with the two transformations and the generated Jacobian or density function from those. Your two estimators look something like that. Now you say, okay, for example, let's say this is a BSDF estimator and this is a light estimator. So these samples say BSDFs, these samples lights. And the question is, how can I combine those two? So whenever this performs bad, we pick this one, let's say, or pick it heavier, like give it a heavier weight. And whenever this performs bad, we'll pick that one. And how you can do that is multiple importance sampling. So you take some functions, so two weighting functions, W1 and W2, that for every x in the domain that you consider, so D in this case, they sum up to 1. So what can you do with this? Well, you have this integral. You say, okay, that's like 1 multiplied by f, and 1, this is equal to 1, so everything's fine. Using additivity, split it into two integrals, and use for this integral, use the first estimator, and for this integral, use the second estimator. And then you get this mix with some weighting functions here. Now you can do the exact same thing for M estimators. So you can see M estimators here, each with 1 over Ni samples, so each may have different number of samples. And you have for each estimator, you have a weight Wi in the exact same way as we did it for two estimators. So how would you choose these functions, Wi? Well, there are various choices. One popular choice is what Veach proposed as a heuristic back when he introduced multiple importance sampling for rendering. And it is really the probability of your current strategy for sampling the integrand divided by the sum of the probabilities. Now, you have some weights here, but you can make those one in the general setting. And we will see that in the code. Let's say, I think at chapter 4, we can start with the code, or also at, and we will also have some code at chapter 5, and we'll see, okay, how do we work with that in code. Also, yeah, something to remember. So here the domain remained similar, but it could happen that one of your transformations makes your domain changes it. So for example, like in the rendering equation, one integral may be of a solid angle and the other may be of a surfaces. In that case, you have to be careful with this probability. So your Jacobians should be with respect to the same thing. So for example, if you're trying to mix a solid angle strategy and area strategy, which would be, say, if you sample lights and you sample the BSDF, that's a problem. And you would have to convert both. There is a way to convert between the two probabilities, but you would have to convert both probabilities to the same measure, so either with respect to area or with respect to solid angle. Questions on that?
Regarding the estimators, I mean,
Yeah.
In the case of MIS, is it necessary for the technique to work that each estimator really estimates a different integrand of this whole integral, or could they, for some reason, relate to the same function? I mean, you talked about
it is the same integral. So you're considering the same integral. You just choose two different ways to compute it. For example, let's say we go back here. Okay, you have this integral, right?
Okay.
Assume for a second you know how to integrate this perfectly, and you know how to integrate this perfectly. So here we showed, okay, if we know how to integrate this perfectly, we can write something like this with something like determinant like this. Then you can get a determinant, a different determinant with a different Jacobian if you were able to integrate f, and then you would get two different estimators. I think I have it somewhere here. Is it? Just a second. Okay, yeah. So let's say you have two estimators. Yeah. You build two PDFs from those. So you want to compute the integral f multiplied by h. You know how to integrate each separately, but you cannot integrate the product of those. Then you build a transformation that has f as a probability density function and h as a probability density function. Then in one case you cancel out the you canceled out the f by considering a probability density function with respect to f, and in the other case you canceled out the h. So now you have an estimator with respect to f and an estimator with respect to h, and you can combine those two through multiple importance sampling. So whenever one is, let's say, bad and the other is better, you would get weights, corresponding weights, so you get the better thing. Does that clarify things a bit?
Yeah, it means that the estimators are for the same integral, but you are actually estimating different integrands. That's it. Different functions inside
yes,
the integral. Okay.
So your numerical integration strategy is different. So it's a different function that you sample.
Okay.
Here it's the same function, but if you use a different transformation T1 here and T2 here, you get something different in the denominator and in here. So you get a different estimator if you consider different transformations or different PDFs.
Okay. Okay. That's fine.
Yeah, for instance, you get f divided by p1 in one case and f divided by p2 in the second case.
That makes them different as
yes,
estimators. Okay.
and one may be, well, if as long as p1 and p2 are different functions, obviously. If they are the same, then it's the same thing. But if these are different, which would be the case, so for example, this would be Brdf sampling and this would be, let's say, area light sampling, then you get a different thing. And obviously one is better for something and the other for something else. Do I have that? I think I have it. But I want to. Okay, he doesn't have it here. Maybe he has it in his book. Okay, say that you have this image here. And in one case, in A, what is this? You sample the light source, right? But the cosine here the angle is very shallow. So you get a very dark thing because you do not consider the Brdf. So it falls like 90 degrees here.
Okay.
Do you get it?
Okay.
So you sample the light, but by sampling the light, you pick directions where the cosine is very small. It's like shallow angles.
Sure. Okay.
Now in the other case, you just sample the, let's say, the cosine, so the hemisphere, not the light. But then here, as you can see, the probability of hitting the light is very small here. So you get a lot of noise here. So in this case, you get noise here, and in this case, you get noise here. And now if you say, okay, I use the balance heuristic or power heuristic to combine the two, so pick the better one in some sense, where it is better, well, you get this, which is nice here and it's nice here. So as you can see, the noise, maybe I should zoom in more. As you can see, the noise here is pretty considerable, and here also. But when you combine them, well, you get the best of both worlds in some sense.
Okay, I'm following.
And
I got it.
multiple importance sampling you can combine many estimators. So if you consider bidirectional path tracing, then you can consider almost a whole selection and then combine all of these or whatever. So here's an example. And you can see if you combine several of those, you get something a lot cleaner. Whereas if you just consider one strategy, well, it's good at some things, but it's bad at others.
Okay.
So I assume that answers your question?
No, that's fine. Okay, thanks.
Okay, other questions? Okay, then in the book, it's a bit axiomatic, let's say, or a bit using kind of postulates, and it starts, okay, say, let's say you have random sequences, then it starts with probability. Well, you don't need probability for that. As you saw, you just need the Jacobian, and you can pick any sequence. It doesn't have to be a random sequence to integrate something. For example, we'll see low discrepancy sequences, which are not probabilistic. So this is an ITC interpretation. Now, if you take the probabilistic interpretation, as we saw before, I think it was here, you can relate the two interpretations, and by saying simply, okay, the probability was actually the one divided by the determinant of the Jacobian of the transformation. Yeah. And in the probabilistic setting, so what you find in the most part of the book, you have the notion of density, you have the notion of expected value, which is simply a kind of average, and you can see, okay, how can I integrate something using the expected value? Well, if you have an integral and you have some density p, you can multiply here. Obviously, this doesn't change anything. It's like multiplying by 1. But this is this here is the definition of expected value of this. And from probability theory, if you have random samples, well, you can approximate this like that if these are random numbers, if xk are random numbers. So it's the same thing said in a different way, but which is valid only for random things. What I presented before, it's valid for, you can pick any sequence as long as the sequence is good in some sense, so uniform in some sense, not necessarily random. Random sequences, they can clump, etc. So not always an ideal thing. Yeah, and this brings me to why you should use Monte Carlo. Well, in the beginning, we saw that our integral is very every term in the solution gets increasingly dimensional, so you get a very high dimensional integral. The nice thing with Monte Carlo, at least for, let's say, non-pathological problems, is that the convergence doesn't depend on the dimensionality of the problem. So your error would always decrease 2 times if you increase the number of samples 4 times, in at least if you've added enough samples. So that's the square root of n here, convergence. The other nice thing is that you do not assume typical integration rules assume, okay, your integrand is smooth or whatever, has derivatives, continuous derivative, etc. Monte Carlo doesn't assume anything like that. It just takes random samples and everything's fine. But at the same time, because it's so general, well, it doesn't make use of such, let's say, smoothness if it is present. There is a, let's say, a trade-off between generality and something that exploits features of smooth integrals, etc. It's using low discrepancy sequences, something like Sobol, Owen Scrambled, Sobol, Houghton, etc. You can find such sequences in, for example, PBRT. And such sequences, unlike Monte Carlo, if you increase the number of samples twice, then the error decreases twice. Remember, in this case, it was 4 times the samples for two times the decrease in error. So this scales nicely linearly. It has a small factor that depends on dimension in the numerator, but that's negligible in practice. And these samples do not clump, so that's nice. Finally, you can go do even better if you know your integrals are smooth, integrands are smooth, etc. You can use blue noise sequences, but those are hard to construct. I don't think there are many that you can pick from, and in general, they don't generalize very well to high dimensions. Questions on that? Okay, if there are no questions, we can go to inverse transform sampling, which is what we use to construct this transformation I talked about. So to get rid of, if you have an integral like that, how can I get rid of that part? Okay, of that part, if I find a probability function that is f of x divided by this, then by the simple fact that my estimator would be fh divided by pf, then this would get cancelled out. You would get an estimator that just has h in it. What would for each? No, so you have a sequence, and let's say you have your pixel. Okay, you pick your sequence and you use it within that pixel. Now, if you use the exact same sequence in the neighboring pixels, that's a problem because you see the correlation between the two, so you see some artifacts in the image. Ideally, you want to somehow decorrelate the sequences in nearby pixels. So that can be done through Cranley-Patterson rotations, which is really, let's say that you have your samples that are in 0, 1 in each dimension. You offset them randomly by a random vector in each dimension, and if they become higher than 1, you just shift them back to 0. So it's something like, let me write it in the chat, I guess, something like this. So yeah, and R here would be your some dimension of your sequence. R and G would be some random number, and you can use that to decorrelate those. Sobo has methods to get a different correlation in each pixel with scrambling. In PBRT, you can check out the scrambling used for Sobo. There are better scramblings. The best one is Owen Sobo, but that's pretty expensive. Yeah. So you would not use a Houghton sequence for each ray, and you would not use the same sequence for each pixel. You can use the same sequence, but you have to modify it in some way, either through Cranley-Patterson rotations or through some scrambling for Sobo, etc. Does that answer your question? You can just write yes in the chat if it does. Okay, I'll assume that it does, unless... Okay, okay. Other people that ask something about no discrepancy, or... I'm not sure I can put a low discrepancy sequence in shaded toy simply because of the memory constraints. It may become too slow. I can try to, though. The problem, for example, with Cranley-Patterson rotation is that they destroy the discrepancy to some extent. So ideally, you want to use scrambling, let's say, for Sobo. And for Houghton, there's also, I think, Fourier scrambling. But yeah, usually you use Sobo. Sobo is generally better than Houghton. Yeah, so that was about low discrepancy. Yeah, I was talking about importance sampling. But sure, feel free to interrupt me if there are more questions. So in importance sampling, you have some function like that. Assume that you can integrate each of those. Then you can construct the required probability density functions to cancel them out by getting a transformation from those. So how does this look like? Well, you just have the probability density that you want. You integrate it in the interval. Then you get the cumulative distribution function. And if you invert that, you get your transformation. So this is really the T that we were talking about. And it by for example, Y here is in 0, 1. You take it, you get your point in your domain of integration, and you use these samples for one, use these samples for the other estimator. And you can, as mentioned, combine the two estimators using multiple import and sampling to get the best results. And here are examples of what the weights would look like in this specific case. So just MIS with two estimators. Yeah. In the d-dimensional setting, nothing much changes. It's quite a bit more tedious, but what you do is technically say, okay, I would integrate all of the, so I would consider some probability density function that I want. For example, I have this function g here. I can just take g divided by its integral, then that would give me a probability density function. I can integrate some of the variables to get a marginal probability density function that is of one variable. When you have something like that of one variable, you can compute, obviously, its CDF. You can invert it to get this variable. Then you can get something with two variables. I won't go in much details with that. We will see it in examples later on, where I use the variable sampled from the first one here. Then I can, if I can invert that too, I can get the second variable, etc. So in general, if you have something that's very high dimensional, you would first sample the first variable, then the second based on the first, etc. And this is just for completeness. This is here just for completeness. You do not have to go too deep into it. Let me see. Okay, these are the examples. Yeah, let's see some examples of that. So in your rendering equation, if you rewrite it in terms of spherical coordinates, a term sinus theta pops out, and you may say, okay, let's just remove that term. So you can say, okay, my probability density function that I want is that one because I want to cancel out this term. The first step, according to this, would be to say, okay, my PDF, it should integrate to 1. So I need to find a C that makes it 1, integrate this thing to 1, and after you integrate it, you can find that, okay, C here is 1 over 2 pi, and this is not a coincidence. This is the upper hemisphere, the unit upper hemisphere, and it has an area of 2 pi. And this would be considered as a constant, basically uniform density. So you have an equal number of points everywhere in some sense. The sinus theta comes from a Jacobian, so you can always, when you look at spherical coordinates densities, you can always, in some sense, ignore that when you say, okay, this is uniform. So this is something uniform on the sphere. You have the normalization factor. So these things I was talking about where, okay, you integrate the first thing, you integrate the second thing. Well, let's see how it works. We have a probability density function of two variables, phi and theta, and we want to integrate one out. And this is the unit hemisphere. So your variables vary from 0 to 2 pi, and from 0 to pi divided by 2. So let's integrate out, let's say, phi. We take this function, we integrate it, we integrate out phi, you get 2 pi. This cancels out here, and the probability density for theta remains as sinus theta. You integrate this out, you get this. Now, if you invert the function, so if I say, okay, R2 is equal to that, then if I move things around, I get the mapping that I want. So now, if I have a random number, let's say 0, 1, I can use that to compute my transformation to theta, and I can do a similar thing for phi, where you get this for the random number. So given this random number in 0, 1, the first one and the second one, you get you can transform it to phi and theta like this, and you have a density of this form. Now, if you want to make a, let's say, array in your scene using that sort of direction, you would take this, so these angles that you computed, phi and theta, and you can use spherical coordinates to construct the direction if you have some orthonormal system based on your normal at the point that you're shading. Questions on that? It's a bit involved. Maybe I think it will become a lot clearer in at least in the implementation. I see there's a question. Computation. So there's a question about if you use sampling for different pixels, generally if you use random numbers, everything's fine. You do not have to care about which samples go to which pixel. It doesn't matter at all. If you use low discrepancy sampling, then in each pixel you would assign a scrambling key, for example, for example, that would transform your sequence so it is decorrelated between pixels. But yeah, I think we'll see that more in the practical application, maybe, if I manage to get in a low discrepancy sequence in there. Yeah, so that was an example of how to sample just uniformly on the unit hemisphere, and this also gave you the transformation from two random numbers to a direction. So that's how you pick a direction if you want to bounce your race around, basically to choose the next uh, direction of the ray after it bounces off something. We can do the same with respect to cosine terms. So in the rendering equation, you have this Lambertian term, the cosine theta, and we can pick the density again, something like this. I won't go into the details here, but the point is, again, using the same procedure, you can get a mapping that, given two random numbers, you can find angles phi and theta with such a density, and then this would cancel out some terms in your estimator. Similarly, you can pick points on the, yeah.
So basically, in the first example, we would get uniform points on a hemisphere, and in the second
Yes.
example, we would get points that are like clamped together,
Concentrated,
concentrated
yeah,
at
around the
the top,
pole,
right?
around the normal.
Oh, okay, thank you.
Because you know that your integral, it has this term there, so you want to cancel out this term, and you cancel it. If you use this PDF in your estimator, the cosine theta term won't show up because it will be cancelled out by the PDF, but by the probability density function. So by choosing a different mapping, you can cancel out terms that you know how to integrate. That's the point. And then also you expect, okay, your error to be lower for even for less samples. We
So
can
we
go,
could use,
yeah,
sorry,
go
we
ahead.
could use the first one and the second one in Lambertian material, but the second one would get
Yeah,
like
so for example, this first one, it would be more noisy than this one.
less noisy.
I can, yeah, I can make an example in this in the shader toy. So you can compare, let's say, the worst possible sampling to the best one for a specific material, and you see, okay, the noise is a lot less if you use this information. This is the point of importance sampling. It's basically, imagine you have a sine function that's oscillating around its average, right?
Yes.
Now, if it's very high frequency, then by sampling it, you don't get very close to the average. Now you say you squash it near its average. So important sampling is basically taking your function and squashing it closer to its average. So when you take samples, the error is smaller. So even for fewer samples, you can get something better. That's the point.
Okay, thank you.
But yes, it does require knowing how to integrate some parts of the integral, or having an approximation of it that you can integrate. And yeah, picking points with such a distribution. We can do a similar thing for the whole sphere. So not just the hemisphere, but the whole sphere. The only thing that changes is the integration is from 0 to pi and not pi divided by 2. And then you get a, where is this? Then you get a mapping that looks like that. So you have 1 minus 2 R2 here. And this will give you points on the whole sphere if you use it here. The previous ones would by having points in, by having R2. So let's see, R2, if it's in 0, 1, this would always generate you points around the normal. So it won't go in the lower hemisphere. Well, this would allow you to go in the lower hemisphere simply because you can have a negative here. What else? Yeah, you can, for example, say, okay, I have a Phong Brdf, modified Phong, so energy conserving, for example, and it looks something like that. So it has a term like this in it. And you can say, okay, I can plug this term in the probability density function, and I can once again compute a mapping for this and a mapping for the second term, so I can sample my Phong Brdf. Yeah. And questions on that? Yes, no questions. Yeah, it would become, I think, a lot more practical with the shader toy examples that's from next chapter. Finally, rejection sampling allows you, even if you cannot construct such a, let's say, such a function here, if you cannot integrate that, or if you cannot invert it, because that's also possible that the function is not invertible, then what you can do is you can say, okay, but nevertheless, I want to sample with respect to some PDF, so some probability density. So what you can do is you can use rejection sampling, which you can see in the book, I think, here, but I'll give you a more, rejection sampling, but I'll give you a more, let's say, immediate example. Let's say that you don't want to deal with that, with these integrals, etc. Technically, you can, using integrals, etc., generate uniform points in the 3D ball, but let's say for a second that you do not know how to. Then you know the equation for the 3D ball. It's if you have a point, so if you have a ball centered around 0, 0, 0 with radius r, then for all points that are inside it, this holds. So their distance from the origin is smaller or equal to the radius. And this is squared just for efficiency reasons. What you can do is you can take then a box from minus r, so the whole thing, some transformation like that. For example, if you have a random number C01 that contains it, then generate points in that box and filter out the points that are inside this. Then you would have points uniformly distributed in your 3D ball. This is not as efficient as what we saw before, but if in practice there are some, as I mentioned, some PDFs that you won't be able to integrate or you won't be able to invert, and then it may make sense to use rejection sampling. Now, what you can do after you have these uniform points on the ball, you can normalize them, then they would be on the sphere. So now you would have uniform points on the sphere. And finally, there's another cool trick, which is if you have a normal that is unit length, you can offset this sphere here with uniform points with this normal. And then if you pick any direction on it, so any point on it, that would have the cosine distribution that we saw above. And you do not need to build any orthonormal coordinate system for that. So you just need the normal. So that's another cool trick. I think it was used in ray tracing in one weekend, but they had a problem. So they didn't map it to the two sphere. They left it in the ball. So the density was cosine cubed. So it wasn't the correct thing, but yeah, it's easily fixed. Yeah, and I think this concludes it. Other questions? Okay, if there are no more questions, thank you for the attention. The next topic, it's a little bit less math and more theory. Basically, we will also see how bidirectional path tracing works, etc. And I plan to start with so I currently have the shader code, the shader toy code, but most people suggested that okay, it should be a bit later. We should use it a bit later. So I think after next chapter, so chapter 4 and onwards, we can start with a unidirectional path tracer. In the shader toy, I have the framework is ready. You don't have to deal with boilerplate, so the RNG is there, etc. Just writing the basic estimator for a unidirectional path tracer. then in chapter 4, in chapter 5, we extended with, I guess, multiple importance sampling, sampling lights, sampling BSDFs, combining those with multiple importance sampling. What else? Maybe bidirectional path tracing, Russian roulette, though this won't make much sense on a GPU, but on a CPU it would. So that's the plan for the next time. Questions? Any questions on? I also added for the last meeting. There are some resources, you can find them in light transport theory. If you go a little back. Yeah. This concludes it. Again, thank you for the attention, and feel free to go.